So I'm going to go through the energy needed to melt ice lab that you did. So we're going to take a look at the data and figure out how we can figure out the heat of fusion for the melting ice that was involved in the lab. So you started out with 100 milliliters of warm water, and then you put some ice cubes in it and you dropped the temperature down somewhere between 4 and 8. So what I did is I came up with just some data here. So starting with the 100 milliliters, after you melted the ice, it turned out to be 161 milliliters total. And your starting temperature, mine happened to be 51 degrees, and the ending temperature after the ice was melted was 5 degrees. And then I pulled out any extra solid ice that was still in there. So by using this data that I collected, I can figure out my heat of fusion down here. So your delta T, or your change in temperature, mine was 46 because I took 51 minus 5. And then from here we can figure out the amount of energy that was lost by your original 100 grams of water. So to do that, we're going to use the Q equals MC delta T equation. So the mass of my original water sample was 100, because 1 milliliter equals 1 gram. Okay, so we had 100 grams of water times C, which is 4.184 for liquid water, times my change in temperature, which is 46 degrees. So if you multiply those numbers out, you get a total of 19,246 joules. So again, you guys have different data, so your numbers are going to be slightly different, which is fine. Just make sure that you use what you had collected in the lab. So now we know that that's the heat lost by our liquid water. So if that's the heat lost by the liquid water, that must also be the heat that was used to melt the ice, right? So now we're going to kind of flip it over. This is the energy of the liquid water. Now we need to take a look at the ice. So the volume of the liquid obtained from melting. So if I started with 100 and I ended with 161, that means 61 milliliters of this was from the melted ice, right? Oops, I just wrote that backwards. Sorry. 61 milliliters. And we know that, again, 1 milliliter of liquid water is 1 gram. So of the melted ice, we had 61 grams. Okay? So we're going to assume that this heat that was given off by our warm water is the amount of heat that was taken in by this 61 grams of ice to get it to melt, right? So now we're going to figure out heat of fusion, and we're going to use two different units for it. We're going to use joules per gram of ice and kilojoules per mole. So to do joules per gram, well, we already have joules and we already have grams, so we're just going to take 19,246 divided by 61. Okay, and that's going to give us our joules per gram. So if you do that, you get a total of 315.51. Now to get kilojoules per mole, we have to do a couple of conversions. So I know my joules, so to get joules into kilojoules, you divide by 1,000. So 19,246 divided by 1,000 is 19.246, right? And to get moles of H2O, if I have 61 grams, I can divide it by the molar mass from the periodic table, and I get 3.39 moles. Oops. Okay, if you do the math here, you get 5.68 kilojoules per mole. Okay, so those are my heat of fusion values. So if you flip to the back of your lab, the first question says the value for heat of fusion is called the latent heat of fusion, and we talked about that before break. And it's the amount of heat required to melt a certain amount of ice, okay? And we know, if we look up in a book or on the internet or whatever, the latent heat of fusion for ice is 334 joules per gram, which means that's how much energy it takes. That's how many joules it takes to melt 1 gram of ice, okay? So quantitatively, how close are your values? Well, we have to take a look at what we got, which was here. This is our experimental, right, from the other side. And we're going to compare it to what we should have gotten. That's called the theoretical latent heat of fusion. So to get percent error, we need to take our theoretical. So theoretically, we should have gotten 334. And we're going to subtract the experimental, which is 315.51. And then again divided by our theoretical. So it's kind of like figuring out how many you got wrong on a test. You would take the total amount on the test minus what you got right divided by the total amount, and that would give you your percent error, right? And always multiply by 100 to get percent. So 334 minus 315.51 divided by 334 times 100 gives us a percent error of 5.54%. Okay? Now, there's a reason why we got some of these errors, and I'm not going to go over that part, but I want you guys to brainstorm with your lab partner as to what could have caused. This is actually a really close value. Some of you are going to be further off than that, and there are reasons for that. And it's, again, we've talked about this before, but it's the way the lab is done that can cause you to have error. So think about the procedure. Think about how you did the lab. Think about the energy, right, from heating up the water to melting the ice, and talk about where these sources of error came from, whether you are able to avoid them or not. If you are able to avoid some of the error, how could you make your error even smaller? What could you do in the lab procedure to get it to do that? Okay, so go through that now. And then lastly, once you guys have that, write a detailed conclusion. What did you do? How did you figure it out? And then talk about your error, sources of error, and maybe what you could do next time to make it better. Okay? Thanks.